In this first video of the Quantum Mechanics for Everyone series, I'm going to start from the very beginning, exploring how the idea of quantum theory first emerged. This takes us back to the late 19th century, when most physicists were relying on Newtonian and thermal physics to understand the world. However, there were still some gaps in our understanding that classical physicists hadn't quite filled. One major gap was how classical physics dealt with the thermal electromagnetic spectrum. Basically, light is made up of electromagnetic waves, each with its own wavelength and frequency. Because the speed of light is constant, changes in frequency affect wavelength inversely. If frequency goes up, wavelength goes down, and vice versa. Electromagnetic radiation wavelengths can range from several kilometers to picometers. A picometer is a trillionth of a meter. Now, let's imagine a hot object emitting red light. The red color tells us that it's emitting a lot of its energy as electromagnetic radiation with a wavelength corresponding to red. It also gives off a bunch of infrared, microwave, and radio radiation. If we introduce a hotter object that emits violet light, we can tell right away that it's hotter than the previous one because violet light has more energy than red light. It also emits other types of electromagnetic radiation, including ultraviolet rays. And if we come across a hot object emitting white light, we know it's really hot because it's able to emit the entire visible and infrared spectrum, along with a lot of ultraviolet radiation, and possibly even X-rays if it's heated to really high temperatures. But what if I showed you a hot object that doesn't glow? In that case, we know that it's mainly emitting infrared and radio waves, with just a tiny bit of shorter wavelength waves, simply because it doesn't have enough energy to emit shorter wavelengths. This is the famous experimental curve for hot bodies, and here it displays the so-called ideal theoretical blackbody radiation density. Note that if the temperature were about 3000 Kelvin, the color of the radiation emanating from the object would be dark red, because it barely covers the red wavelength of the visible spectrum. But if we raise its temperature to 4000 Kelvin, for example, the peak will shift to the left and fall at the shorter wavelength corresponding to the orange color. If we raise the temperature to 6000 Kelvin, the thermal glow would be white because most of the electromagnetic energy would be emanating in the visible field. On the other hand, the dashed line on the right represents what the classical theory of Rayleigh and Jeans predicts for this thermal radiative emission. Each wavelength on the x-axis represents a group of electromagnetic waves from the blackbody, so each wavelength is called a mode of vibration. In classical theory, each wavelength or mode has the same average energy, which is kBt. Because of inverse proportionality to the wavelength, which is raised to the power of 4, the classical curve rises rapidly to high values of energy density. At short wavelengths, it becomes very high, indicating that the object will contain very, very high energy. Hot objects will not withstand this and will melt immediately. This clearly contradicts the experiment, which is why it is called the ultraviolet catastrophe. The problem is that there is nothing in classical theory that determines the shortest wavelength. If we wanted to calculate the total energy of the body, we would integrate from 0 to infinity. We will thus obtain infinity. The solution to this disaster was proposed by Max Planck, and it was by dividing the energy of a single mode in the system into an integer number of energy quanta. Quantum is indivisible, and its energy is proportional to the frequency of this mod, where h is a constant. This means that each wavelength on the x-axis will have an energy of nhf. N is determined by calculating the average power of each mode and will be given as follows. The first factor is the energy of a single quantum, and the second factor is the number of these quanta in a single mode, and it depends on both the temperature T and the wavelength lambda of the mode. So, instead of only kBt in the classical theory, we now have this. I want you to focus on the exponential term in the denominator. At short wavelengths, this term will become large. Therefore, the denominator in the red box will become large, and thus the entire fraction will become smaller. If the wavelength approached 0, the denominator would become very large, and thus the fraction would become very, very small. This means, at short wavelengths, there will be no energy to excite the modes, and so the energy curve drops to zero. Thus, we got rid of the unrestricted rise of the energy density curve, and the curve became consistent with experiment. This was the first problem solved by quantization, and was the first step towards what is now known as quantum theory. Please subscribe and push the like button. This will help the channel to grow. Thank you.